Okay, welcome again, everyone. Now, our next speaker is, sorry, I won't read that, Ryan Orendorff.
Cool. Yeah, hi guys. My name is Ryan Orendorff. Actually, before I start the talk, I wanted to just say some thank yous. So I know that this is the last LambdaConf. I've been attending them ever since I actually missed the first one, so I'm a little bit sad about that. But I've been attending them ever since, I believe, the second one. And they've really made a big impact on my life. So when I originally came to these, I was actually in grad school doing something very different than programming. And I fell in love with functional programming through this conference and the people who kind of attend. I've learned so much through everyone that's been here. I've really made some good friends. And so I kind of just wanted to have a thank you to LambdaConf for hosting something that's been so impactful to me, for having such great friendships, for getting to meet you, John. And it's been really great. So I was hoping that we could all give a round of applause for the LambdaConf. Okay. Great, so with that, I will now actually get started with my talk, which is a little bit different than the title that you saw before. So the title is going to be, Don't Panic, You Too Can Write Programs That Process Encrypted Data. So let's talk about how data is normally secured in traditional applications. So normally, we trust third parties to keep our data safe. And one of the things that happens is, like, as part of this trust model is that the user will have some sort of data that they want some online application to process. They'll send this over to a server, usually through a HTTPS type protocol or something that essentially encrypts the data so that no one in between, in the perfect case, can actually intercept and read the user data. The server will then process this data into some result and return it back to the user. But all of this processing actually happens in the clear. So once the user passes some data, they can be relatively assured that that data will get to the server in an encrypted format and it will be safe in transit, most times. But once it gets to the server, you're really trusting the operator of whatever application that you're using will actually try to hold your data safe. So what's kind of examples of maybe applications we might want to talk about? So classic examples, if you're using some sort of online shop, say Amazon or whatever, the user has, in this case, the private data is what you're buying, for what amount, what credit card you're using, that type of thing. So the server needs to know that information, specifically in plain text, so they need to know the actual decrypted data in order to process your request. And then also maybe an example that happened somewhat more recently or in the last few years was if you had some DNA service, they would, I guess, actually take your DNA through the mail, but the other parts related to your ancestry were uploaded online. So you'd be trusting some DNA service to process your data about your ancestry. So the question is, can we trust third parties with our data? So I would say that there's kind of three broad cases that we want to consider when we're dealing with third-party data. One is data misuse. So maybe one of the highest profile cases of this is data profiling, and specifically we could think about the Cambridge Analytica scandal. So what happened in that case is that the data was misused in the sense that it was given to parties that shouldn't have had it. So that data had some value, and then essentially by being not secured enough and being passed off to other people, it could be mined for extra value that the user did not intend. So my doubt is that most people who, in this case, used the products wanted their data analyzed by Cambridge Analytica. There's also the case of just malicious actors. So say we have, there can be cases where I mentioned, so we have HTTPS, but people can still do what are called man-in-the-middle attacks. So essentially someone could post, as in this case, say Equifax, and forward all your requests to the actual Equifax website. But in the meantime, you send them all your data and they have the unencrypted version. So then they can use that data to log into Equifax on your behalf, freeze your credit, screw up your credit, that type of thing. And so these first two cases are maybe like cases of, well, one's an attack and one is a misuse by the actual company. But we can also just have plain old data breaches. So in this case, what we would have is, say, 23andMe. 23andMe a few years ago accidentally exposed DNA and kind of related personal information through a data breach. So in this case, we can assume, or I was assuming, that they tried their best to secure the data from actually being leaked from their services. But unfortunately, they didn't actually protect it well enough, so their application was hacked, and people were able to steal that data. So that's even a case where, you know, the application developer for the website you're using is trying their best to actually protect your data, and it's still not necessarily safe. So the takeaway here is that even if we trust third parties to do the right thing, our data is not safe once we've passed it off to another party. So maybe then the question is it even possible? Can users keep their data privacy while still using their favorite apps? Their 23andMe's, their Facebooks, their Amazons, these types of things. Well, I have a talk here, so that's why we're talking about this. So yes, we can. And specifically, we can do it using this cool cryptography technique called fully homomorphic encryption. So what is fully homomorphic encryption? Let's break it down in kind of the two pieces. The first part is the homomorphic encryption itself. So that allows data to be processed while remaining encrypted. Maybe, for example, what you want to do is add two numbers. So what the homomorphic part means is that this equation that we have here holds. So either I can take two values, an A and a B, and I can add them in plain text and encrypt them, or what I can do is I can encrypt an A, I can encrypt a B, and then add the ciphertext. Ciphertext is another word for encrypted data. And then I will get the result is the encryption of A plus B. So if we like commuting diagrams or category theory, maybe the arrows will be helpful. So either we can kind of take this top path. We can either do A plus B and get a resulting A plus B and then encrypt the result, or we can go down the first two arrows. Take A to encrypted A, B to encrypted B, add them, and the result is the same. We still get encryption of A and B. So it doesn't matter which path you take there. And actually what's kind of fun is you can also kind of mix and match here. You could take an encrypted A and add it to B and get an encrypted A plus B as well. So the last part of this term is called fully. So that means that any computation can be performed on encrypted data. So in the sense it's like some variant of Turing complete, we're not necessarily saying that it will be reasonable to execute any program. Some of them might take a long amount of time or a large amount of space, either on disk or in memory. But essentially, you should be able to execute any program in an encrypted form. So let's look again at kind of our traditional application that we'd have. So remember, in our traditional application, we would have a user sending data to a server through, in this case, an HTTPS protocol. And the server would then process that data. So anytime you see red here, that's unencrypted data, that's plain text data. The server will then encrypt your data and send it back to you through the same channel, and then that way the user gets the result. So they'll get the confirmation that you bought something or whatever it is. So now let's look how this changes with an FHE-based application. So in an FHE-based application, the user first encrypts their data. So you can see here there's actually a little key between the first part of the data and the second, where now when you see green text, we're dealing with encrypted data. And specifically on the kind of there's a dashed line there that separates the user and the server. That key doesn't ever get transferred. So the user always has access to that key, and they are the only ones with access. It allows them to both encrypt and decrypt the data, but otherwise no one can do anything with the ciphertext on the decryption front. So the user now has that encrypted data. They then send that through the channels that you're familiar with, the HTTPS, to the server. But now the server has encrypted data. They don't have that key that the user has. So they actually can't ever decrypt it. Even if they were like, it got misused or stolen or whatever, it means nothing to anyone except for the user. But with FHE, we can do that bottom arrow. We can do data to the results, and then send the result back to the user where they can decrypt it themselves. So in this case, the user is in control of their data privacy. So why don't we just use FHE all the time? Well, current FHE setups are difficult to use. So the user needs to know cryptography well in order to choose the right systems and parameters. So during this talk, we're going to be talking about what's called torus FHE, which is based on torus elements. So for that one, you need to know what toruses are. And then there's also a scheme called BFV, there's BGV, CKKS. These are all different ways to do FHE applications. So the question is what are the trade-offs? Well, you really need to be a cryptographer or like adjacent in order to really understand. And then even inside these systems, it gets difficult. So one of the things that's important to FHE is usually you have, not always, but you have like a polynomial. So it's maybe the size. When you're trying to encode a message into a polynomial, how big is that polynomial? What is the modulus for the elements in that polynomial? You add noise in this case for any of these FHE, well, in any cryptography system, but in particular FHE. So then the question is, how much noise do you add to your ciphertext such that you can still do some computation without actually corrupting the results? So that part's very difficult. Making the computation performant is difficult, even for experts. A large parts of this is just the fact that there's a lot of FHE primitives that you're keeping track of, and trying to figure out exactly how to coalesce them in the right way and use all your cores at the same time, that type of thing is quite difficult. As I mentioned also, you can get incorrect results if you process the data incorrectly. So all of the ciphertexts have this property called noise, which is in a sense what gives you the security in FHE. But it's a double-edged sword, because what noise also does is if it grows too large, and it grows every time you do any sort of FHE operation, addition, multiplication, that type of thing, that noise grows. If it grows too much, it essentially overrides the message in your ciphertext. So now, say, instead of doing A plus B, you would get the result of A plus B plus some random number when the user tried to decrypt it. So you wouldn't actually get the result you expect. And finally, the other challenge is that it's hard to translate problems into FHE primitives. So, FHE primitives are often defined in terms of circuits. So you're dealing with something more similar to maybe hardware-style logic, or they come down to something that's essentially just addition and multiplication. So the question is, how do I write WhatsApp with addition and multiplication? That is kind of a hard question to ask, right? So it's hard to translate, take whatever problem someone's working in their business logic and actually convert it into an FHE primitive. So to solve that, we have the Sunscreen FHE stack. And here's where I try to sell you as to why you should do this. So with the Sunscreen FHE stack, you can easily write your own secure applications. You can keep the users of your applications safe from hackers, and you can look darn cool in the process. And you can even claim that you're doing post-quantum cryptography, because FHE is all post-quantum. So you can get yours today. Everything is open source. It's open source under the AGPL v3 license. So we have a GitHub that you can go to. It's github.com/sunscreen-tech. So I'm going to describe the stack a little bit. So what makes up the Sunscreen stack? So first, there's the FHE primitives. So at Sunscreen, we've developed actually our own variant of what's known as the Torus FHE scheme in order to be performant. It's all written in Rust. And we use that for the low-level primitives of FHE operations. These are things such as bit-level operations, an operation called bootstrapping, which allows you to reset that toxic noise that I was talking about, and those types of things. Then on top of that, we built a processor that runs FHE primitives optimally. So it tries to use as much as, it's a virtual processor, so it's not just a single core, but it tries to use essentially all of the compute power that's on your machine in order to run an FHE program optimally. And finally, the processor, even though you're not writing FHE primitives, you would be writing in an assembly language. And assembly languages are not fun to write in. So we've modified the LLVM compiler such that you can write programs in C and then compile to the FHE processor that we have. OK, so the general idea here, the general tagline is BYOP, bring your own program. So how do you program? Parasol is the name of the processor. So how do you program a Parasol FHE program? Well, the first step is you write a program in C. Then you'll add some annotations about some encrypted properties of your program, which specific functions you want to compile, whether or not an input is encrypted or not. And then you can run your program with our virtual processor. Now, for that, you'll need to use Rust in order to actually run it. And then the final steps are up to you. So essentially, this is where we have the gnome that's saying, you can now wrap up some FHE small application or bigger application, and now you need to figure out how to deploy it and actually put it into a Web 2 or Web 3 case. So let's go do this. So we'll see how all this works, but we're going to live code this. So together, all of us are going to build our first FHE program. Cool. Here I have just kind of a basic setup. I just have VS Code open, or actually, sorry, this is the Z editor. I switched recently. Also, great editor. This is a kind of standard cargo bin setup. So it's a binary that we're going to run. Eventually, we're going to fill this out, which is going to run our program. But in the meantime, I have this folder called FHE programs that we're going to write some C into. So the first program, or the program I really want to kind of just show is a really basic one. I just want to add 2 numbers. So I guess in the room, how many people are familiar with C? I know it's not functional. Okay, everyone, perfect. Okay, awesome. So you probably know how to write add then, but we're going to go through it anyway. So the first step is that we're going to include the standard int library. The reason why we're doing this is that we're going to have to specify the size of the numbers that we're going to add. So in this case, we're going to do 8-bit integers. And then the next step is we're actually just going to do the thing, draw the owl. So if you're familiar with C, you start off with the return type. The return type for add will just be uint8_t. We define its name. We then take in 2 inputs, which we will call A and B. And then I'm sure you guys, we all know how to write this part. We just want to add the 2 numbers. So we are going to return A plus B. OK, so that's all you need in order to write the add program. So I haven't done anything exciting yet. You're probably like, well, that's a little boring. I'm going to go through a little bit of a diversion of what this actually looks like for people who are unfamiliar as to when say, this computer that I'm operating on right now, what it does when it tries to execute this program. So what we're going to do is I'm actually going to go into this. So I have my add.c program, and I'm going to compile it with the version of Clang that came with this computer or got installed by Xcode. I don't actually know which part installs Clang. But when we call Clang, we're going to call it in a specific way. We're going to call with our add C program. So that's the program we're going to compile. We're going to add some optimizations. That's what the O2 stands for. The -c is important because it says that we're not going to link this against any other file. And then we're just going to actually compile it. So that's great. I mean, yeah, we just compiled a file. But what does it actually look like? So we can use this utility inside LLVM to actually dump the assembly that's inside this file. So here, what we can see, I'll have to resize this a little bit, is that our add program got turned into very small instructions that this specific ARM-based computer can run. So what happens is, the way to read this, if you're unfamiliar, so ARM processors have, or this particular one for V8, has 64-bit registers, which are small parts really close to the core of the CPU that allows you to actually deal with values. So the smaller version of those are called W registers. They're just aliases. So the first instruction that we have, if we tried to execute this program on this M2 computer, would be to add the 0 in the first register and store it in the 8th register. And then we do this additional operation where we're ANDing. So it's a little bit odd, but essentially it's a 32-bit add, but because we could have arbitrary numbers in there, you basically just only select 8 bits, and then we're done. So that's all we have for a program. So I've gone through, like, how do you do it normally? So now let's go through how we make an FHE program. Well, the way we're going to do this is we're going to first add attributes. So you might have seen these before. Sometimes they look a little bit different, but this one we're using the double bracket notation. So you first specify what program you want to actually turn into the encrypted format. So here we're saying that we're going to turn add into an FHE program when we run it. And then additionally, there's one other thing that we need to do. So, and this is used essentially for some of our analyses, is that we need to specify whether or not the inputs are encrypted. So by default, we would say that they're just plain text, which is fine. You could have Parasol run plain text data. But there's an annotation here that just essentially allows you to specify that the inputs themselves are encrypted. So my editor reformatted this a little bit onto like a line break, but that's it. You have now written your first FHE program. This is all the transformations you need to do in order to convert a regular C program into one that operates on encrypted data. So I will say congratulations to us all for doing the first part. The second part is how do we actually run this? So normally what you would do is you would have a main function, so a main.c. And what that would do, oops, I can spell, is it would do some sort of type of run your add function. So we would say add A and B, and then you would say like printf the result, and you would fill this in with whatever way you wanted to print it out or do whatever, right? So we're going to have to essentially emulate this part in Rust. So this is the part that we're going to use to actually run our FHE program. great. So let's go to our Rust program. So here, I'm going to do a few things first. Well, actually, I'm going to describe the way that we're setting this up. So essentially, if you remember from this part, we need to do a few different steps. The user first needs to encrypt data, then send it to the server. Then the server needs to actually process our data, send it back, and then we'll do encryption. So we'll be doing those steps in those orders. So here are the steps. The user does encryption of data and sends it to the server. And then the server will process it, that returning the data. And then finally, the user will user decrypts things. OK, great. So let's actually get started with implementing this. So the first thing I'm going to do is, we saw in our C program that we had used an 8-bit integer. And we need to essentially define that inside of our Rust program. So I'm just going to use this as a little bit of a helper. But currently, our compiler supports unsigned integers, but we have working support for signed integers in the next release, which should be coming up soon. So you define a type uint8, an unsigned encrypted 8-bit integer, using this specific uint type. And here you specify a size and along with a ciphertext type. So ciphertext type is not too important in this case, but essentially it's a reference to the FHE often has, or sorry, Taurus FHE specifically has ciphertexts are stored in various forms. So in this case, the one you'll most likely be dealing with is called a GLWE ciphertext. The 8, I want to kind of just quickly mention, here it's a const generic in Rust. So you might be thinking like, oh yeah, you can only do like 8, 16, whatever bits. But actually, here you can specify a smaller number of bits. You can specify 7 bits. You can specify 24 bits, all those types of things. So you might want to choose a number that's not exactly a power of 2, because say, for example, you were processing something and you knew the value was between 0 and 127. Well then, having that extra encrypted bit will add a little bit of overhead to your runtime, so you might want to choose a different number. But anyway, in this case, we're going to stick to 8-bit integers. And let's get started with the user side. So the user side, the first part is that we need to generate that key that I've been showing. Luckily, that's pretty easy. So if we want to generate the secret key, we can use this secret key object or type, struct, and then use it with this generate default parameters. So this is all you need to generate a key that the user can then use to encrypt and decrypt data. Now, one thing I want to note here is that there's this with default parameters. It's not just generate. So I had mentioned that it's very difficult to choose the correct parameters. And luckily for everyone in the room, we've spent some time doing a lot of simulations and stuff like that to figure out what are the optimal parameters that would get you good security along with good performance and very low error rates. So in this case, this default set of parameters is 128-bit secure with an error rate, I believe, close to 2 to the negative 40. So there's a very, very, very low chance that your computation will fail. It'd be like, you'd have to run several universes time and sort of something to fail. And additionally, we've chosen it such that like it has the smallest amount of size and it can run most performantly. Okay, great. Now, one thing that I haven't quite talked about yet is that I've said that the server can process data, but not exactly how. So there's actually another part here. They need something called a compute key. So the compute key, as you can probably guess, also has a struct. And that one, you can generate that one with the default parameters as well. Actually, I'm going to change the secret key just here briefly to we're always using the secret key as by reference. So that's what the little and sign means. So this just generates a compute key. So if you're familiar with cryptography, specifically public key cryptography, usually you have more than one type of key, one of which allows you essentially to either encrypt data or do something to data but not do the decryption. This key is similar. This key is safe to send to anyone to process encrypted data because it doesn't give you the ability to decrypt anything. All it gives you the ability to do is run an FHE program itself. So with that, we need to define a and a B for the user. So we'll say, like, let's do the addition of 4 and 5. Now, encrypting the data is very easy. We're going to say the encryption of A is that uint8 that we had before. And what would you know? There is an encrypt function that, oh, I need one more part, which is the encryption parameter themselves. So in order to encrypt data, essentially all I need is the value that I want to encrypt. So in this case, I'm going to say A. A reference to the set of encryption parameters that define the scheme that we're using, and then the secret key. So that's all you need as the user in order to generate this encryption. This should be secret key. That's all you need to do that. If you want to encrypt B, which we will, then it's of course the same. Actually, I'm just going to copy these two lines and just change the A's to B's. Okay, cool. So this is kind of the end of what a user would do. So they've defined some values. They've encrypted them. And at this point, they would pass off the encryptions of A and B over to a server. So now the server needs to do two different parts. It needs to first load a file. So I'm actually going to include a file up here. If you're familiar with Rust, you can essentially include a file in the actual runtime binary itself, or you could include the bytes of it. So I'm going to call this add FHE, which is a reference to a list of bytes, as using this include bytes function. And then I'm just going to define here, one thing I didn't quite do here is actually compile it for us. Sorry. So when we want to compile it for us, we use Clang again. But in this case, we actually want to define a target. So here we're going to define that we're going to run on the Parasol CPU. And it does the same thing. And let me briefly just kind of show that the instructions are actually different. But it's doing the same thing. So remember before that we were essentially doing the add and then selecting the bits we want. The Parasol processor works a little bit differently. It's a little bit closer to the RISC-V processor. So what it does is it will first truncate the registers down to 8 bits from 32 bits. Then it will do the add, and then it will do a 0 extension. But these numbers here are essentially the bytes that I need to get to in order to run the actual program. So when I'm saying include bytes, what I'm doing here is I'm going to be able to reference those directly. There's one final step in here, which is just you can actually bundle multiple files together using LLD. So I'm going to say here that what I want to do is include the bytes of the FHE program /compiled /add. Cool. And then one thing that's nice about Rust or the Rust language server is it actually, since it goes and checks that that's there, and so it would give me a little red squiggly if it couldn't find it. So the server will need that file, and additionally, it will need to package up the arguments for that it's received from the user. So we have this thing called an arg builder, which uses the arg builder pattern. But all you need to do is add arguments. So here we would say that the server would get the encrypted A. It would get an argument for the encrypted B. And then it's still of type arg builder. What we need as an output type is arguments. So we have to basically specify what the return type is. So here we would say that the return value is going to be an 8-bit integer. So that's all the server needs to do in order to get a set of arguments. And then now let's get to actually running the program. So I've defined, or a long time ago to make this easier, a nice little utility function called creatively run program. So run program takes in that compute key. Remember I said that was required. The actual file that we're going to run. It requires a name. So the name is essentially the name of the function. So as I've kind of mentioned here on the left side when I was compiling multiple files together or even just defining multiple functions inside a single file, you could have multiple of these FHE programs. So I'm going to have to say which one I wanted to actually call. So for that, I'm going to say that I'm going to want to call the add function. And then we've defined the structure that wraps the arguments. And then that's it. That's all you need to run the program. We know that it returns a result, so we're going to get the encrypted result here from running our program. Now, one of the things that's nice about any of the modern editors is they also kind of show you what the type will be. So if you're familiar with Rust, you've probably dealt with the result type. But essentially what it is either this computation could succeed and it just works, the processor's fine, or it could fail, in which case it will tell us that it actually, like, there was a problem. But in this case, we're just going to call this thing that you should never usually use in production code called on the wrap, which just says that I know that the actual program will succeed. So after that, the idea would be that you would send back the encrypted results to the user. The user can now say, get their results by saying encrypted results dot decrypt. And then here you pass in those same encryption parameters and the secret key that we defined before. OK, great. So this, actually, I'm going to add one more thing. Result of encrypted A plus encrypted B equals encryption of result. Right? So that was the equation that we had before, which is to say that we should be able to follow this particular thing, and I'm just going to print it out. So this follows the, remember we have all the parts now. We've encrypted user data, we've sent it over to the server, we've used the compute key in order to run the program we've defined, and then we return those results and decrypt them. So now, if everything works properly, I should be able to run this. So as you can see here, it's running, and it tells you that the, oops, I forgot a friend there, but the result of encrypted 4 plus encrypted 5 is an encrypted 9. So that's all I needed to do in order to write a program that takes in this case, it's not taking in A and B, it's taking in the encrypted versions of A and B and actually doing that addition for us. So yeah, that's kind of it for the main parts of like how you actually write your first program. Now, I'll talk a little bit more later in the talk, but you can essentially think about the compute key is cacheable, so you try to figure out as developing an application where to store this type of thing, the set of library of functions that you'd want to be able to run. You'd have a bunch of these calls to run program, passing in the compute key, and a method by which to keep track of whose ciphertext belongs to who and who's to return to who, that type of thing. Great, OK. So with that, I'm going to go back to the presentation. So we've done it. We've made our first FHE program. And I wanted to, I've actually talked about this before, so I wanted to talk a little bit through kind of some of the properties or things that you can do in these C programs. So they're not unlimited in the sense of like we don't support a few different things, but there are quite a few things that last time I mentioned at LambdaConf that were not possible. So I said it was not possible to compare encrypted values. Last time I said it was not possible to have unlimited computation. And what that means is that you can run a program of arbitrary length. In the previous version of the compiler we had, which actually used the BFE scheme, as you can see in the slide, you could essentially only run a program up to a certain amount before we knew that the ciphertext would be corrupted. So you had a limited number of operations you can do in the prior one. And also, there were some operations that were leaky. So you had to be careful that you wouldn't say, if you subtracted the ciphertext A from itself, you would get the trivial encryption of 0. You would just get all zeros. If you, say, multiplied by 0, you'd have a similar thing. You'd have a ciphertext that was all zeros. So those were all problems. And I'm happy to say those are no longer restrictions. With the move from BFE to TFHE, and with our new compiler and processor system, we can actually do all of those things that I've said. So let's talk about some of those. We can compare encrypted values. So let's go through a particular example here. I'm not going to live code anymore. I'm glad that worked out. So say we had some sort of account that we were trying to charge as a bank or some sort of service where they had a balance, and we wanted to subtract an amount from that balance such that we could pay ourselves or just deduct it from them. So for this particular program, what we're going to say is we actually don't return anything, and we take in the balance as a pointer. And then we have this property where we figure out what amount we actually want to subtract. So one of the interesting parts about FHE is that I can't necessarily have an if block on an encrypted condition and do anything arbitrarily on the side. What I have to do is I have to use essentially what's underneath the hood called a CMUX operation but otherwise use the ternary operator. So here I can compare two values, encrypted values, amount and balance. And if the person has more than the amount in their balance, then I could subtract out the amount that I want to take. Otherwise, I'm going to set that to 0. So that's going to say that essentially I'm still going to perform an operation here later, the subtraction, but I'm actually going to subtract 0 because I couldn't withdraw that amount. I don't want to underflow the value. And then the final step of this program is that I'm actually going to update the balance, the pointer to the balance itself, a piece of memory, and reduce the transfer amount. So remember, in this case, by using the encrypted comparison we had on the second code line inside the actual body, we were able to specify, we were able to compare the amount and balance and only subtract the amount if the person had the amount to subtract from, or subtract from their balance. So this example shows kind of like two different things, that encrypted comparison and the updating a memory location. So that's kind of fun. We can also inline other functions. So one of the great parts about programming and not programming assembly is that we can write modular code, right? So as programmers, we probably want to write libraries and pieces, separate functions that do small utilities that we can test independently. So in our FHE program, we can actually inline other functions as long as they're specified with inline. So here we have a function called getBit. So well, what getBit will do is that essentially we'll take a bit string, in this case packed as a uint32 value, and it will subtract, it will find a specific bit inside there and will return that to you. So that's that end number. Yeah, and then what we'll be able to do here is that, one thing I guess maybe to also know here is the get bit, we've optimized the compiler to like specifically handle this case and produce even more efficient answers for this particular program. But say we want to run this price item program. So what this will do is it will figure out the price of an item based on a set of discount flags that someone might have. So a user would pass in, or maybe the company would pass in the base price of, say, a pair of shoes, and then they would also apply, the user could apply a set of discounted codes, and they would be packed into this uint32 value. So we can now use this inline function to, say, get the 0th bit. Maybe the 0th bit of the discount flags is that you have a store membership, so you can do get a discount for that. Maybe you have a coupon discount, so you've shown that you had that. You can then get that from the first bit. And then here what we do is we just take the base price that we have, and then we use those the comparisons that we had before on Boolean values to figure out, well, either I subtract 2 for the store membership or 3 from the having a coupon to the price in order to return a final encrypted price that the user will actually pay. So this shows like a powerful value in that you don't just need to run or define your FHE programs and kind of live in only FHE land. You can write other utility functions and test them just like normal C code. And actually what's kind of fun about this code is you could actually run it on the Parasol processor, just plain text. So you can test all your stuff in plain text, make sure it works, use your own testing library, framework, whatever, and be able to build the modular code and like well-tested code that you want. The other part about this example is that it mixes two different types of values. So we have the base price itself is unencrypted, whereas the discount flags, what a particular user has to apply, are encrypted. So here, you just mix them freely. The result will be an encrypted value. Whenever you could think of encryptedness as being pervasive in some senses. So anytime you do a plain text and an encrypted operation, you always get an encrypted result. But you can mix and match freely. So you should always expect the output of this type of program to be an encrypted value. And finally, one of the other things that we can do is that if you happen to know the size of the loop, we can actually unroll it for you. So inside, and this is something that came in with LLVM and Clang, is you can specify, say, for this Hamming distance calculator, which just calculates how different two bit strings are. You can calculate basically how far they are by going over each bit, extracting each bit, and then if the bits are different, you'll say that their distance from each other is 1 greater than what you were looking at before. So here, the for loop, you're going from I equals 0 to I is less than size, where size was defined earlier, say to be 64. Use that if condition. Normally, so if conditions are a little funny, so normally we try to use the ternary operator. Clang is an amazing piece of technology and will also sometimes do things I do not expect. So sometimes it will turn those if conditions into like very weird things, so I don't use them as frequently. And then we return the encrypted distance, Hamming distance between these two pieces. Great, so with that, I want to show some demos. and I'm going to hope that my internet works. So the first demo I'm going to show is something related to dark pools. So one of the things we talked about was, say, buying something online. But another important financial aspect is trading. So whether or not you're buying and selling stocks or any sort of thing of value there on a market. One thing that can be interesting is that, say you're a large institution and you want to trade, say, 1 million stocks at like a very high value, maybe $500 million. If you try to sell that on what's called the lit market, which is the market that we're all using usually when we're on Charles Schwab and Robinhood and stuff like that, is that you can't actually get enough like sellers to buy that thing immediately. And even if you did, essentially the market would shift so much while you're trying to do that transaction that you would not get the price that you wanted. So inside traditional markets, so like regular financial markets for stocks and equities and stuff like that, there are these things called dark pools. Dark pools essentially are run by people who will keep all of your transactions private and will handle the way to pair one sort of bid and ask, bid and sell between different clients while keeping all the information secret to everyone except for themselves. So, but that's the key part, is that the except for themselves. So there have been cases where people operate dark pools and then they use the fact that they're the only privileged person to this information to front run you. So what that means is they know you're selling 1 million units of whatever, and they're gonna be like, I see you're dumping all of this stock. I'm going to dump earlier than you, so that way I get the better price now before it potentially craters. So in a truly FHE dark pool, what we should be able to do is even the network operator, the person operating the dark pool, will not know what the transaction content is. So for this one, I will go to the dark pools demo. Oh, this is interesting. Well, anyway, every time I reload this graph, it's like crypto markets are kind of, which way is it going? But it's going way up more than I expected. So this particular dark pool example uses our FHE technology. What we have here is just kind of a graph of, this is just for plotting. But the main part here is that you can essentially produce encrypted transactions. Here we see that we have an encrypted order book with some sort of encrypted prices that already exist. But we're going to actually operate on this market ourselves, on this dark pool. So I'm going to want to sell for a very odd amount of money. I'm going to want to sell or spend 1 Bitcoin to get 1 Ethereum. Now, if you're familiar with crypto, that is way not the price at the moment. I mean, you can see it right now. It's 0.0025. So this is not the value. Do not make this trade. But like, essentially, we're going to like encrypt it and submit it to the order book. So what happens here is it's submitted successfully. And then it will show up here as a list of orders. So say I'm client A, I submitted this thing. What you can see here is that the operator, there's these decrypts. It's very tiny, unfortunately, but these little decrypt texts. Those ones are just for us while we're debugging, while we're looking. But otherwise, the operator of the dark pool would not know the price that I asked for on this trade, would not know the amount, would not know how much it was filled, like if their order had partially been filled, whether or not that had happened. Now, say I'm client B, who was willing to do this trade at the same value that you specified. I can submit my sell order, and then what will happen is that the encrypted cases will cancel each other out, and we'll see that actually both transactions disappear. So at no point, we know that the transaction was fulfilled completely. We don't know how much it was for. We know it was for Ethereum to Bitcoin, but we don't know any other information. And there's even kind of things here that are cute in the sense of, like, say I want to submit an encrypted order, and I want to sell, this is, oops, 0.5. I want to sell half an ETH for 1 Bitcoin. Here, what will happen is I submit that successfully. This order still won't update. You won't see actually a change here. But if we actually decrypt this value, oh man, that's really hard to see. But we can see it's 50% there. So if the runner of the dark pool, the person who's actually operating it, would not see this, but you would be able to check that your actual order was 50% filled. And then we could submit another order, and then the actual value would go away. So those transactions have been completed. That's how you do a kind of basic dark pool-based example. So in this one, the order book could, say, be in Web 2 or Web 3. So in this case, the kind of backend is more of a Web 2-based model. Now let's look at, Now let's look at a different example. So this one, we're going to show FHE in an on-chain application. So in an on-chain application, what happens? So no native chain supports FHE, of course. So we need to be able to provide FHE operations to that chain without necessarily modifying the chain itself. And the way that we do that is we use this thing that we've dubbed a data bus, an off-chain data bus, which is very similar to an oracle. But essentially what it does is users will submit what they want to happen. So they'll say, like, I want to run, in this case we'll be doing an image convolution, but I want to run this program with these particular encrypted inputs, and they will create an event. Our data bus will then listen for that event, will then run the program for you, and then the user can then choose whether or not they want to decrypt the result. So there's an encrypted result, but otherwise they'll choose what they want to do with that. So for those unfamiliar with, I've just stolen this from Wikipedia, for those unfamiliar with image convolution, what you do is you take a kernel, here it's a 3x3 matrix, and for every pixel in the image, you select its neighboring pixels, in this case it's neighboring 3x3 pixels, and you multiply pointwise that kernel by all of the neighboring pixels, and then you sum up the results in order to get a filter on your image. So in this case, the identity one's not too interesting, you just get the image back. If you say change it to this kernel where it has -1s and 5s in it, you actually sharpen the image. So the image lines will appear sharper, anything that's a little blurry, you'll have ideally more detail. It's obviously not you can't infinitely sharpen, this isn't CSI, so like there's a limit there. So the way that this works is, this is the GIF also from Wikipedia. So this is where it's showing, kind of going over each element where you sharpen it. But at the start, you can see there's the kernel and an origin point, and you're centered in this case on that 7. So it does a pointwise multiplication of every value in that image, and then adds the result, comes up with the 9, and then that's in the output image. So again, essentially what we're going to be doing is we're going to be showing how to run this program in Web3 using our data bus that we have. So we're going to essentially need to do a few things. We're going to need to write our program. We're going to need to wrap it up in an Ethereum smart contract. So the demo I have is running on Sepolia, which is a test network for Ethereum. And then we're going to need to deploy that to the blockchain, and then we'll watch what happens. So, oops, for this one, we're going to launch the HPU. So this is, for this demonstration, essentially it's like a version of VS Code that we've written into a web page just to make it look like what the developer experience would look like for someone using this data bus service. So here we would define our program, our FHE program that we have before. So in this one, it's called execute pixel. It's that convolution, that's that single convolution operation where we're doing the neighborhood of pixels and we're summing the result. So in this case, our next version supports arrays, but at the moment, for the version of the compiler I'm showing, we didn't. So we're taking in every pixel, in that 3x3, along with a output pointer. And we're just going to multiply every pixel in that image by a corresponding kernel. So in this case, we've chosen a kernel that's a little bit arbitrary. I actually don't know what the image would look like with that one, but it's just something that's kind of filled with dummy values for now. So you'd multiply every value, and then you would sum the values and return the result. So as someone who wanted to, say, put this onto the Sepolia test network, I would first need to compile this file, the same way we compiled the other add file. You'll get, this is just a different way to show the actual bytes inside that file. It's just a whole big bunch of numbers. And now what we'll need to do in order to use it on chain is we'll need to actually wrap it up in Solidity. So Solidity, if you've used it before, it's not a functional language, but it is an interesting language that allows you to run smart contracts on a blockchain, specifically an Ethereum-based blockchain. So what happens here is that you would upload your convolution program, these bytes here that you got from compiling. You would upload that to our data bus service. You would then get back an identifier. That identifier is, in this case, a 256-bit number. And you would also need to reference a specific function. So like before, we had specified that we had the execute pixel function. So in order to actually, say, execute this program on chain, what we'll need to do is we'll have to define an execute function that takes in the actual values we took for those pixels in a neighborhood, packages them up in a little bit, and then send an HPU request. So HPU stands for Homomorphic Processing Unit. It's another name for the data bus that we have. And what will happen is once a block is mine that has run this execute transaction, our data bus will pick that up and actually run the program that you've specified by that hash. And return, and when you do this, you'll get also a run handle. So that handle you could use to query whether or not the program was finished running or whether or not get the encrypted results or decrypted results. And the final part of this is that we have a decrypt function. So the decrypt function essentially allows you to specify that you're going to take that run handle and you're actually going to ask for what's called a threshold decryption. So a threshold decryption is, you could have users decrypt a value, but in another application where maybe you have a distributed key, you can actually distribute the responsibility among n parties such that the majority of them need to work together correctly in order to decrypt a result. So it's very much like a blockchain style thing where you can have distributed trust. So here, let's look at an example of actually like running this. So I'm just going to fill this in with random values. Convolution is that running that execute function that we had before. If I confirm this, you can see I've actually sent a transaction to the Sepolia test network. So this is all running live on that test network. We'll then wait for that convolution to complete. And then the one thing that's, now we can decrypt the answer. And actually, I'm just going to start this decryption and then going to talk. So it actually takes a while to run this, and it's not because the FHE program runs really fast. The reason why it takes a while to run this is you need a block to be mined in order for the data bus to pick it up. And blocks are only mined every 12 seconds. So this whole process happens over 3 blocks. So I need to wait at least 36 seconds for this process of asking for an execution, asking for a decryption, and then posting the results of the decryption. So here we get the number 48 returned to us. And then specifically when we ask for a decryption, we do it through a callback. So you specify like the threshold decryption committee will be able to call your contract on chain and will give you a value that you can then post in your own contract. Cool. And then that's that demo. So I think I'm coming close to time. So I'm going to run through these next parts. So performance. What is the performance of this type of thing? So there's generally 2 different ways to measure performance in FHE programs currently in the literature. One is essentially a test of cardiac health. So you can take parameters related to, say, someone's blood pressure and these types of things, and you calculate for each time some value or set of values is in an erroneous zone. You basically increase the risk factor by 1. And then if that can tell you how much risk you have for an adverse cardiac event. So for that, we have this FHE program, which just says that, like, given some risk factors and weight, age, your lipid levels, the height, physical activity, how much of a risk you have for a cardiac event. We also have this other program called chi-squared, which is just a statistical test that calculates the association between some variables. So the last one did a lot of comparisons. This one does a lot of actual numerics, so that's why we have those 2 as benchmarks. And what we see here is that the Parasol programs are fast, versus these are a bunch of other FHE compilers, Concrete, the Google transpiler, which is named Hare, or they have another one, Hare's the new one. These other ones all take over a second in order to run. Ours, we can run for chi-squared in 610 milliseconds on a large AWS C7G.16x large machine. So we're not winning in the memory department because actually most of that memory usage is the compute key. It actually doesn't change between the programs. But what we can see here is that oftentimes we're like at least 3 times faster, in some cases hundreds of times faster than, say, like Juliet or E3. And then additionally, our compilation is fast. So we're able to compile these types of programs in under 100 milliseconds, and the actual instruction size and byte encoding of this information happens in a very small number of bytes. So here, both cases result in this case, 1/4 of a kilobyte and 1/2 kilobyte of space. So with that, together, we've all written our first FHE program. I've ideally tried to show you that the Sunscreen FHE compiler makes it easy to craft privacy-preserving applications for any developer. This enables you to reduce the chance of malicious data use, reduce the effects of data leaks, and give users control of their data. So finally, if you have any questions, I'll take them. And the reason my dog has become the company dog, specifically this photo where she wants me to take her on a hike. So that's why that photo's there. So it's my talk.
Thank you very much, Ryan. We have one question. I guess we have time for only one question.
So you probably get this question a lot. If you need Rust to kind of like orchestrate all of these operations using like your libraries, and both Rust and Clang have an LLVM backend.
Yeah.
So what motivates the choice to write these FHE programs in C as opposed to Rust?
Yeah, that is a very good question. So essentially, actually, Rust uses a forked version of LLVM, but our processor, in some respects, will work with anything that could produce LLVM IR intermediate. So we could support Rust and all these other types of things. In order to get essentially to the MVP, Clang is built into the LLVM project, and so it's a little easier to modify and get it to support C. But we do want to support Rust coming up because it can also compile to LLVM IR, and then you'll be able to replace this with just all Rust instead. But it's a great question. It's mostly just Rust needs a few more pieces than we've currently defined.
Well, thank you again.
Cool. Thank you.